All right, so let's look at some examples of these approximate tests. So the first example we're going to look at, example 2.4, is a large sample right-tailed test. So the data on the next slide are a random sample from a distribution with unknown median. The question of interest is whether there is sufficient evidence at the 0.05 level of significance to conclude that the median of the distribution exceeds 60. Now we want to use the large sample test based on the normal approximation to the binomial distribution in answering this question. And so here are the data. We've got 30 observations. I've got some summary statistics calculated down below. So the sample mean is 64.3167. The sample standard deviation is 9.5885. Now this notation here I'm using to represent the sample median. The median of the sample is 65.2, and then EXST, which again is counting the number of observations that are greater than the hypothesized value, which is 60. EXST is equal to 18. Okay, and so here are the hypotheses. The null hypothesis says that the population median is no more than 60. The alternative hypothesis says that the population median is greater than 60. All right, and that's what we're trying to show, so that goes in the alternative. The rejection criteria using a 0.05 level of significance, and again using this approximate test, is to reject the null hypothesis if zcalc, the standardized version of EXST, is strictly greater than the upper fifth percentage point of a standard normal distribution, which, as you know, is 1.645. The calculated value of the test statistic, zcalc, is 2 times EXST minus the sample size all over the square root of the sample size. And so 2 times 18 minus 30 all over the square root of 30, that turns out to be 1.10. The p-value of the test, because this is a right-tailed test, is equal to the probability that the standard normal random variable is greater than or equal to the observed value of zcalc, which is 1.1, and that probability turns out to be 0.13567. Now we get that from the standard normal table. We don't have to construct the sampling distribution, the binomial distribution for n equal to 30 and p equal to 0.5, and then evaluate the CDF for that distribution and all that. So you see that this is much easier, much more straightforward to do. All we have to do is take a look at the standard normal table to get our critical point, or if we're using the p-value method, we would use the standard normal table in calculating the p-value. And so what is our conclusion? Well, I've drawn a conclusion using both methods, the test statistic and critical point method, and the p-value method. So utilizing the test statistic and critical point method first, because zcalc, which is 1.1, is not greater than 1.645, we fail to reject the null hypothesis. Using the p-value method, since the p-value, which is 0.13567, is not less than or equal to the specified level of significance, 0.05, again we fail to reject the null hypothesis. So using either of these methods, we fail to reject the null hypothesis. And so in stating our conclusion, we say that there is insufficient evidence at the 0.05 level of significance to conclude that the median of the distribution is greater than 60. So again, this is what we call a large sample approximation to the exact test using the binomial distribution. We're using an approximation to the sampling distribution, and that approximate distribution is the standard normal distribution. Now, a sample of size 30 is not necessarily huge, especially when we're talking about approximating the binomial distribution. So it's questionable as to how accurate this test is, and so we might want to consider this. So how do these results compare to those that would be obtained using the exact test based on the binomial distribution? Well, so let's go through that process. Let's perform the test using the exact sampling distribution, the binomial distribution, and compare the results. So if the boundary condition of the null hypothesis is true, then as we know, the test statistic EXST will have a binomial distribution with n equal to 30, which is the sample size, and success probability p equal to 0.5. So that is the exact sampling distribution, the exact reference distribution to use for this test. And the next slide shows information about this sampling distribution. All right, and so if I look here, I've got, you've seen this kind of a slide before. Here I've got on the left panel, I've got the instructions on my TI-84 calculator to construct the sample space for this distribution, and then to construct a column or a list containing the values of the CDF for this distribution, and then the third column contains values for 1 minus the CDF. And so you see here in list 1, I'm showing values from the sample space. It's not list 2 contains values of the CDF, and then list 3 contains values of 1 minus the CDF. So again, the hypotheses we're testing. The null hypothesis is that CAP-M is less than or equal to 60. The alternative is that the population median CAP-M is greater than 60. The problem said to use a significance level of 0.05, which, when we're dealing with a discrete reference distribution like the binomial, there may not be a critical point that gives us exactly a significance level of 0.05, as we've seen, so we need to keep that in mind. And so what we'll do in this situation is we'll look for the closest significance level that is no larger than 0.05. So this is a right-tailed test. We're going to be rejecting for large values of the test statistic. And so in terms of critical points, we're going to reject the null hypothesis if x tot is greater than 19. All right, so let me go back here to the previous slide and let's see where we got that. Remember that list 3 here contains 1 minus the CDF. And so the values in list 3 correspond to the probability that x tot is strictly greater than whatever value is in the same row in list 1. So for example, if we scan down the values of list 3, we're looking for the greatest number that is less than or equal to 0.05. And when we get down to this row here, we see 0.0494. So that's just about 0.05, but not quite. All right, and the value in list 1 that corresponds to that is 19. All right, and so again, this is the probability that x tot takes on a value greater than 19 if the null hypothesis is true. And so that's where we get this. Now, because of the discreteness of x tot is greater than 19 if and only if it's greater than or equal to 20. So we can state the rejection criteria in either of these two ways. Okay, in terms of the p-value, we would reject the null hypothesis if the calculated p-value for the test is less than or equal to 0.05, which in this case, because of the discreteness of the binomial distribution, is equivalent to rejecting the null hypothesis if and only if the p-value is less than or equal to 0.0494, since that was the closest attainable significance level that is less than or equal to 0.05. Okay, so again, for this example, we found that x tot was equal to 18, so that's the number of observations in the original data set that are greater than the hypothesized value of 60. The p-value is therefore probability that x tot is greater than or equal to 18, and that turns out to be 0.18080. Again, we can get that from this lower right panel here. So the probability that x tot is greater than or equal to 18 is equal to the probability that x tot is strictly greater than 17. And we see that that's 0.1808. We can also calculate it using the CDF function, as I've done here in the right panel. So 1 minus the binomial CDF evaluated at 17. What I'm doing here is just using the formula that I gave back when we looked at right-tailed tests, using the exact sampling distribution. All right, and so the conclusion, what was the rejection criteria? Well, if we can state it two ways, if x tot is strictly greater than 19, or we could say if x tot is greater than or equal to 20. All right, since that's not the case, since x tot, which is 18, is not greater than or equal to 20, and also since the p-value is not less than or equal to 0.05, there is insufficient evidence at the 0.05 level of significance to reject the null hypothesis and conclude that the median of the distribution is greater than 60. Now we're saying here there's insufficient evidence at the 0.05 level because of the discreteness of the distribution and because the closest attainable significance level is 0.0494, we would be completely justified in saying that there is insufficient evidence at the 0.0494 level of significance to reject the null hypothesis. But it may be more beneficial to say 0.05 here because it's more relaxed. Again, when you fail to reject it's okay to leave that at the 0.05. Because remember, the larger the significance level that you say you're using, the less evidence you're requiring in order to reject the null hypothesis. Why are we doing this? Again, we're wanting to compare the results that we got from the large sample test and the exact test. So the p-value of the approximate test based on the normal approximation to the binomial distribution, that p-value was 0.13567. The p-value based on the exact test is 0.18080. Now again, just let me reiterate that the test that we're using, this test based on EXST, this is the correct p-value. This is the exact p-value. The 0.13567 is an approximation to this 0.18080. And we're obtaining that approximation using the approximate sampling distribution. So in general, if we were going to go ahead and use the binomial distribution, we would just get this exact p-value and not bother with the approximation. But what I'm doing here is showing both methods so that we can evaluate, we can assess the quality of this approximation. All right? So let's evaluate that using the relative error. So the relative error of an approximation is equal to the approximate value minus the true value. Then we divide that difference by the true value and multiply by 100%. And so the relative error of the approximation in this case, it's about negative 25%. And the negative sign tells us that the approximation is too low. So the approximation here is about 25% too low, and that's really not very good. However, remember this is a large sample approximation, and we only have 30 observations in this case. So the fact that this approximation that we're getting here is not very good, that should not be too surprising. In general, as we've seen in our other coursework, in particular when we've worked with the normal approximation to the binomial, we know that approximation gets better and better as the sample size gets larger and larger. And so we might expect, and I think reasonably so, that if we were to use this approximation procedure for larger sample sizes of 50 or 100, 150 or whatever, that the approximation will, in general, improve. Now, one thing to consider, instead of looking at the relative error, let's look at the absolute difference, the absolute error. And again, I won't take the absolute value of the difference because the sign tells me whether my approximation is too high or too low. All right, and so the absolute difference, the approximate value minus the true value, is negative 0.04513. And so we get a sense of the quality of the approximation by looking at that difference as well. So neither of these would be very good. All right, now let's look at a left-tailed test. This is example 2.5. All right, and so in this example, we're going to increase the sample size a little bit. And so we'll have a sample of size 50 in this example. So a random sample of size n equal to 50 was selected from a distribution with unknown median. Now I'm not going to list out the observations because the sample size is getting a little bit too large for that. But I do give summary statistics. The sample size again is 50. The sample mean is 73.536. The sample standard deviation is 7.5977. The sample median is 74.05. And then EXST, which again is counting the number of observations that are greater than the hypothesized value, which we'll indicate here in a second, is 22. So the question to be answered is whether there is sufficient evidence at the 0.05 level of significance to conclude that the population median is less than 75. All right, so we see the hypothesized value 75 here. So EXST is the number of observations out of the 50 that are greater than 75. And we're told to use the large sample test based on the normal approximation to the binomial distribution to answer this question. All right, and so the null hypothesis says that the population median is greater than or equal to 75. The alternative hypothesis says the population median is less than 75. That's what we're trying to show, and so that goes in the alternative. At a 0.05 level of significance, using this large sample approximation for this test, the rejection criteria is to reject the null hypothesis if the calculated value of the test statistic z-calc is less than negative z sub 0.05. So if it's less than negative 1.645. The test statistic, z-calc, is 2 times x tot minus n all over the square root of n. So 2 times 22 minus 50, 44 minus 50, all over the square root of 50. And so that's about negative 0.85. The p-value, because this is a left-tailed test, is equal to the probability that the standard normal random variable z is less than or equal to the observed value of our test statistic, z-calc, which is negative 0.85. And that is equal to 0.19766. And again, we get that from the standard normal table without having to construct the particular sampling distribution, the binomial distribution with n equal to 50 and p equal to 0.5. We don't have to go through that process. All right, so what's the conclusion? Well, utilizing the test statistic and critical point approach, since z-calc, which is equal to negative 0.85, is not less than, it's not to the left of, negative 1.645, we fail to reject the null hypothesis. If we're using the p-value method, we would say since the p-value, which is 0.19766, is not less than or equal to 0.05, we fail to reject the null hypothesis. So in both cases, again, obviously we're going to come to the same conclusion using either of these because they are equivalent. So in this case, based on the data, based on this large sample test, there is insufficient evidence at the 0.05 level of significance to conclude that the median of the distribution is less than 75. Again, I want to emphasize that this p-value that we've calculated here is an approximate p-value. And going back to the previous slide, this critical point is an approximate critical point for a 0.05 level test. And the reason that these are approximate is because the standard normal distribution is just an approximation to the sampling distribution of z-calc. Again, let's do this test using the exact procedure and then compare the results with the results that we got from the approximate large sample procedure. All right, so in this case, the null hypothesis is that the population median is greater than or equal to 75, and so if that's true, and in particular if the boundary condition is true, then x tot is going to have a binomial distribution, in this case with n equal to 50 and p equal to 0.5. And then on the next slide we've got useful information regarding this. This is a left-tailed test, and so using x tot as the critical point, we're going to reject the null hypothesis in favor of the alternative for small values of x tot. And since we want to use a significance level of no more than 5%, we see here, looking at the list 2 values, the list 2 contains, as you can see here, the binomial CDF values. We're looking for the largest value in this column that's less than or equal to 0.05. Right, and we see that that is going to be 0.0325, and that corresponds to a value in list 1 of 18. And so that gives us the critical point for this exact test. Right? In terms of the critical point, we're going to reject the null hypothesis if x tot is less than or equal to 18. In terms of the p-value, we would reject if the p-value is less than or equal to 0.05. Again, which in this case is equivalent to rejecting if the p-value is less than or equal to 0.0325, since that's the closest attainable significance level for a left-tailed test in this situation that is less than or equal to 0.05. So again, the calculation of the test statistic, there were 22 observations that are greater than 75, so x tot is 22. The p-value for the test is therefore the probability, because this is a left-tailed test, and because x tot is equal to 22, the p-value is equal to the probability that x tot is less than or equal to 22, which we can get either from this page, all right, and so we see here the value there, 0.2399, or we can evaluate the binomial CDF just with that value and get that p-value. In drawing the conclusion, we can say since the test statistic x tot is not less than or equal to 18, or equivalently, since the p-value is not less than or equal to 0.05, there is insufficient evidence at the 0.05 level of significance to reject the null hypothesis and conclude that the median of the distribution is less than 75. So qualitatively, in this case, we're drawing the same conclusion as in the large sample test. All right, but we do see that there are differences. There's a difference in the p-values that we obtain using the approximate test and what we obtain using the exact test. All right, and so what we want to do is we want to calculate the relative error. And so the relative error in this case is not quite as bad. It's only 17.6%, negative 17.6%. So that's still not good. That's not very good at all, really. But we're moving in the right direction. Part of the reason for that, I would imagine, is because we have a larger sample size. We've got a sample size of 50 rather than 30. And as we were saying, the normal approximation to the binomial distribution gets better and better as the sample size increases. All right, and so we would have expected this to be somewhat better here. Notice that in real terms rather than relative terms, the difference here is it's about the same, about 0.04228. And so finally, let's do one more example. We'll do a two-tailed test, a large sample two-tailed test. Again, when I say large, I'm not saying that the sample is large. What I'm saying is that we're using a procedure that's meant to be used for large samples. In this example, though, we do have an even larger sample size. So in this example, we're using 100 observations. So we've got a random sample of size n equal to 100. It's been selected from a distribution with unknown median, cap m. Summary statistics for the sample are given next. So we've got n equal to 100. The mean of the sample is 152.5395. The standard deviation of the sample is 12.8511. The median of the sample is 153.49. The question of interest is whether there is sufficient evidence at the 0.05 level of significance to conclude that the population median is different than 150. And so once we know that hypothesized value, we can compute x tot. So out of the 100 observations, there were 61 that were strictly greater than the hypothesized value of the population median, 150. And so we want to answer this question using the large sample test based on the normal approximation to the binomial. And as we've done in the previous two examples, we will also perform the test using the exact procedure and compare the results. All right, so we've got the hypotheses for our two-tailed test, and the null hypothesis says that the population median is equal to 150, and the alternative, the population median is not equal to 150. We're told to use a significance level of 0.05, and I'll interpret that as being no more than 0.05. And so for this large sample test, because we have a two-tailed test, we're going to reject for either small values of our test statistic or for large values. All right, and so we're going to reject the null hypothesis if z-calc is either less than negative 1.96 or if it's greater than positive 1.96. Now the calculated value of the test statistic z-calc is 2 times x tot, so 2 times 61, minus the sample size, 100, all over the square root of the sample size, and so that turns out to be 2.2. The p-value is twice the probability that a standard normal random variable is greater than or equal to the absolute value of the observed value of the test statistic, z-calc. It's twice the probability that z is greater than or equal to 2.2. And we get this 0.0139 again from the standard normal table. We have to multiply it by 2, and so the p-value for this test, and again, this is an approximate p-value for the test, is 0.0278. All right, so let's state our conclusion. So using the test statistic in the critical point, since a z-calc does meet our rejection criteria, since 2.2 is greater than 1.96, we reject the null hypothesis. Alternatively, we could utilize the p-value, and since the p-value, 0.0278, is less than or equal to 0.05, again, we reject the null hypothesis. And so in this problem, we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the median of the distribution is something different than 150. Let's do the exact test and then compare the results. So that we're doing this to get a sense of the quality of the approximation that is provided by this large sample procedure. So again, if the null hypothesis is true, then X tot has a true sampling distribution of the binomial distribution with n equal to 100 and p equal to 0.5. The following slide contains useful information about this. Now again, we're going to be rejecting for either small values of our test statistic X tot or large values. And we want the combined tail areas to be no more than 5%, 0.05. And so I think you can look here and see that the critical points that are going to give us a test that has a significance level of no more than 5%. The lower critical point will be 39, and the upper critical point will be, well, depending upon how we state it, either 60 or 61. You'll see what I'm talking about in just a second. But if we do that, then the overall significance level will be 2 times 0.0176, which is a little bit less than 0.05. If we were to go up one more on that lower critical point, 40, and down on one on the upper to 59, we would get a significance level that's about 5.6%, so a little bit too big. Okay, so using the exact sampling distribution, the rejection criteria in terms of critical points would be to reject the null hypothesis if X tot is less than or equal to 39, or if X tot is strictly greater than 60. Now, the upper criterion is equivalent to rejecting if X tot is greater than or equal to 61. All right, so let's go back to this previous slide. Where am I getting that? Well, remember that list 2 has the binomial CDF. So this 0.0176 corresponds to the probability that X tot is less than or equal to 39. Down here in the lower right panel, looking at list 3, again I see 0.0176. And that corresponds to, remember that list 3 contains 1 minus the values in list 2, so 1 minus the CDF. So that 0.0176 represents the probability that X tot is strictly greater than 60. All right, and so that is where I get this statement here. So we could state the criteria, the combined criteria, either in this way, or for the upper endpoint we could say if X tot is greater than or equal to 61. Okay, in terms of the p-value, we would reject the null hypothesis if the p-value is no more than 0.05, which in this case, again, because of the discreteness of the binomial distribution, the exact reference distribution, this is equivalent to rejecting the null hypothesis if the p-value is less than or equal to 0.0352, which is the closest attainable significance level that is less than or equal to 0.05. All right, so X tot was 61. The p-value turns out to be 0.0352. And so since X tot is greater than or equal to 61, and also since the p-value is less than or equal to 0.05, there is sufficient evidence at the 0.05 level of significance to reject the null hypothesis and conclude that the median of the distribution is different than 150. Now the other thing is, based on the p-value, since we're rejecting here, it would probably behoove us to say that there is sufficient evidence, not at the 0.05 level, but at the 0.0352 level, because that's the actual level that this test is, that we can perform this test at. All right. So again, before we finish this up, we want to compare the p-values. All right, so we can compare these two procedures, the large sample procedure and the exact procedure. So the approximate p-value using the large sample procedure was 0.0278, and so this 0.0278 represents an approximation to the true p-value from the exact reference distribution, which is 0.0352. All right, and so let's calculate the relative error. We see that, wow, it's negative 21.02%. So the approximation here is 21% too low. The relative error went up, didn't it, from the last example? Even though we doubled the sample size from 50 to 100, the relative error the magnitude of the relative error actually got bigger. Well, we'll talk about that in a second. But let's look at the actual difference, okay, not the relative difference, but the actual difference between the two. And we see that that difference between them is the negative 0.0074. So the actual difference, the magnitude of the actual difference did get smaller, but the relative error actually got bigger. Now, let's talk about why this is. All right, even though we doubled the sample size from the last example to this example, why did that relative error get bigger? Well, it's because we're further out in the tail. Okay, the p-value in this example is smaller. The results are more significant than they were in the previous two examples. Remember that in the previous two examples, we failed to reject the null hypothesis. In this example, we're rejecting. We're rejecting because the result is more significant. In other words, the p-value is smaller, further out in the tail. Here's why the relative error actually increased, even though the absolute or the true difference between the two values is closer to zero. In thinking about the normal approximation to the binomial distribution, whenever we talk about that, we say for sufficiently large sample sizes. Now, what is sufficiently large in this context? Well, a lot of times we'll say that the approximation will be adequate if both n times p and n times 1 minus p are greater than 10. And they actually are in this case, aren't they? N times p, 100 times 0.5 is 50, and so is n times 1 minus p. So those are both quite a bit bigger than 10. But the place where you see the approximations being not so good, even for a sample size of 100, are out there in the extreme tails. If we were calculating central region probabilities, those approximations would be probably be quite good, all right? But anytime you're utilizing a normal approximation to the binomial, the situations you need to be careful about in approximating those probabilities are when you're calculating very small probabilities out in the tails. And in order to get really, really accurate approximations out in those tails, you need to have even larger sample sizes. So that, here we had 100 observations, but because the p-values are so small, because we're out there in the tails, the approximation is not as good as if we had a larger sample size. So that just shows that doing these kinds of tests, if you are using this large sample approximation in this testing situation, if the p-value is small, you need to take it with a grain of salt and realize that it may not be accurate. And that's especially true if you've got a smaller sample size. If you've got a really, really big sample size, then obviously you can put more confidence in that p-value. But keep in mind that this large sample procedure it's an approximate procedure. It's giving us approximate p-values, and it's giving us approximate critical points. Okay, so that is the end of this lecture video. I'll stop it here, and we'll continue on with some new material in the next video.